All right, we're going to transition now to the renal system for the remainder of today's class, our last class. And as repeated from a moment ago, the renal system does cover 2 chapters. And we're really just going to pick out a few highlights about the kidney and how it functions. So we won't go so much into the buffering and etc., which is clearly important for the job for the kidneys, but we're just going to understand how they work, right, in general. In chapter 18, what we're going to do is just look at some major functions of the kidneys. We're going to look at the structure of the kidneys and then spend most of our time on the nephron structure. And then we'll look at how urine is formed. Okay, so this will be a review from this week's lab. And if we look at the renal system, the kidneys may do more than maybe what you realize that they do. And what they do is they affect the plasma ion concentration, keeping it hopefully in set point. So they also, right, in addition to altering the ion concentration in our plasma, it directly affects the blood volume of our plasma, which we have an idea about when we talked about chapter 6, when we talked about aldosterone, antidiuretic hormone, cardiovascular system, chapter 13. Okay? So we have an idea the kidneys can actually change our volume of blood. It also, therefore, affects the pH of the blood plasma, which we know then affects the overall tissue, right? pH. Everything's kind of interconnected, if you will. Additionally, the osmolarity, okay, the fluid volume balance of our cells are influenced by the action of the kidneys. But probably what you're most familiar with about the kidneys is that they get rid of excessive waste, okay, like urea, ammonia, hydrogen ions, we got too much bicarbonate ions, or etc. We can get rid of those types of products. That's certainly not an all-inclusive list, but it gives you an idea that our kidneys do more than just get rid of waste. They get rid of excessive things to keep our blood plasma in set point for ions and etc. If we review the anatomy of the renal system, the kind of main players of the game include the kidneys, right? We have a pair of kidneys. I guess we're designed or built generally to have 2 kidneys, but certainly people might develop differently. So we have 2 kidneys. They are not exactly, I guess, parallel with one another. The left side is a little bit higher than the right side. In addition to the kidneys, we have the ureter. The ureter, what does it do? Urine drains to the bladder. Takes urine from the kidneys to the bladder, right, for storage. And then the bladder, right, would temporarily store the contents, and when it's time to micturate or go to the bathroom, the urethra, right, would be the last kind of portion of the renal system for excretion. So clearly we're going to look at a little bit better detail of the kidney and then within the nephron. So let's zoom in, looking at figure 18.2 at some better detail of the kidney. If you've been in lab already, you may recognize some of these structures. If you're coming to lab today, we're going to do a dissection. We're going to look at some real kidneys. They've already been cut up for us, but we'll get to handle them. There are 3 primary areas to a kidney. And I think I just have the show from the textbook, so maybe you don't want to have to label everything, but let me outline them. There's 3 major areas to just the gross anatomy of a kidney. The first is called the renal cortex. The cortex means what? The outside. The outer portion of the kidney is called the cortex. And it's in this lighter shaded area. In the renal cortex is where you'll find the glomerulus and a lot of our arterioles, and the convoluted tubules will be up in there as well. Additionally, the innermost portion of the kidney is called the what? The medulla. Okay, the renal medulla. Remember, we've been using the word medulla a lot this semester, so you got to precede it with what structure you're looking at. Okay, so the renal medulla is this inner portion, so this is arcing, right? This is one little segment. So this whole, where these little pyramids are, the little triangular shaped areas. This is the renal medulla. In the medulla is where you'll find the loops of Henle for your nephrons. Okay, so the nephrons span the cortex and the medulla. The third primary area of a kidney is called the renal pelvis, and the renal pelvis is this big yellow fan-shaped looking structure here. So this is called the renal pelvis. When you look at it in their dissection, it'll just be like real white, dense connective tissue in there. All right, so the renal pelvis is the third area of the gross anatomy of the kidney. What do you think the renal pelvis does? That's where the collecting ducts drain into. So what's it collecting? The waste. The waste. Well, and you could call it urine by the time it is in the renal pelvis. So you could just say it collects the urine. We'd only want to use the word urine after, right, from the renal pelvis on. We won't use the word urine upstream, right, from the blood or whatever the case, or in the tubes. And then we'll zoom in on this nephron to label it in just a second. Before I move on, what questions do you have about the basic structure of a kidney in the three major areas? The cortex, the medulla, or the pelvis? Within the kidney, between the cortex and the medulla, as identified, are guesstimated upwards of about 1 million nephrons. And the nephrons are referred to as the functional unit of the kidney. What that means is this is where this urine formation starts, here at each nephron. So they're tiny, they're microscopic, but their structure is really critical to our understanding of how the kidney functions. So that's why we're going to zoom down to this microscopic level and look at a nephron. So if we looked at figure 18.3, looking at a nephron, a generic looking nephron, just to remind you, like any picture we've seen all semester, this is some artist's rendition. They could have drawn it this way, they could have flipped it over, they could have turned it upside down, they could have tangled it up upon itself, okay? So it's kind of stretched out a little bit so we can appreciate the structure a little bit. In the yellow are the tube component of the nephron. And only just a small bit of the blood vessels are actually shown. So some detail is certainly missing about the nephron, but we want to look at the tubes before we look at the blood. The blood supply is critical to the kidney. If there were no blood supply to the kidneys, we would never filter the blood and we would never form urine. So the blood is important, but I want to look at the tube structures first. And so since it kind of looks kind of crazy, it can be a bit daunting to look at, but I think there's something that's kind of landmark or characteristic. What is landmark or characteristic to you about looking at a nephron? What might be a good landing point to kind of figure out your orientation? The glomerulus surrounded by the Bowman's capsule. So one of those two structures are a great place to kind of start. Okay. So the glomerulus does not look labeled here, but the glomerulus, what is the glomerulus? That's where it gets all the stuff.
That's where the shoes are.
That's where stuff gets filtered. You say shoes?
Yeah.
What do you mean? The podocytes?
We call them shoes, yeah. That's what they are, right?
The podocytes is a term of the cells that surround. What are these? The word I'm looking for, what is this thing? If it filters, it's a set of capillaries. And the capillaries do have podocytes around them. So the glomerular capillaries are the capillaries, so their job is to filter. And of course, the capillaries receive specific blood flow via arterioles, and we'll elaborate on those. If you want to, you can go ahead and label them in this image. The afferent arteriole is going to be the one that has a bit larger lumen diameter. Can you see that tiny difference in the diameter between the afferent and the efferent arteriole? The afferent arteriole has a larger diameter than the efferent arteriole. Just go real fast. Real fast. We get yeah. No. Yeah, I'll disagree with that. Okay. Surrounding the glomerulus, in the tube compartment is the Bowman's capsule. So the Bowman's capsule is just this kind of like glove-looking thing that surrounds. What is its job? To collect, to capture the filtrate. The Bowman's capsule is there to capture our filtrate that's formed at the glomerular capillaries. And then once the filtrate is collected by the glomerular capillaries, it's going to flow through. There's a really high pressure, fluid pressure, just pushing this blood plasma and forming filtrate. And so the filtrate will travel through our tubes, kind of like water goes through a sink. You have a higher pressure and more controlled, if you will. And certainly our pipes, these are cells that metabolize and exchange, etc. And so you want to maybe draw an arrow outward to represent that filtrate pushing out. Okay, we're pushing out away from the glomerular capillaries, but it's trapped inside of these little tubes. And then when filtrate is pushed away, it hits a very specialized set of tubes. What is the next characteristic tubular structure that the fluid will encounter? It's called the proximal tubule. Your book drops the word convoluted, but it is convoluted, so it's twisty. So we have a lot of what? Surface area. We have a lot of surface area. So this first area would be the proximal tubule. So filtrate passing being pushed through the proximal convoluted tubule. What happens here at the proximal convoluted tubule? Reabsorption. At the proximal convoluted tubule, filtrate is reabsorbed to where? It's going from the tube it's going back in the interstitial fluid. The rest, anything that's not reabsorbed, stays in the tubes, then goes to the loop of Henle. But if we are reabsorbing something from the filtrate, we're taking it out of the filtrate. We don't want to lose it, so we're putting it back into the blood, the interstitial fluid, and then back into the peritubular capillaries, which are not shown on this image. So the proximal convoluted tubule has a bunch of transporters to reabsorb useful substances like glucose, sodium, maybe even potassium. I keep naming your hormones, right, etc. There's a lot of transporters there. Filtrate, if it's not reabsorbed, it continues through its journey, so then it hits the what? Descending limb of the loop of Henle. So label this right side. And I know this right side is the descending limb, so I'm seeing it pushed. So maybe need to draw an arrow here as well. Fluid pushing down the descending limb of loop of Henle. And label it as such, the descending limb of loop of Henle. Let's see if I got this shown. What happens at the descending limb of loop of Henle? Very good. You see a high proportion of water reabsorption. Water reabsorption is specialized here in the descending limb of the loop of Henle. What hormone do you think can have an effect on my descending limb of the loop of Henle? Very good. Antidiuretic hormone. Can target here. All right, y'all are on it, so I'm going to quiz you. Where did that ADH come from?
Subdural.
No, it comes from the hypothalamus.
Cortex.
Yeah.
Oh,
Very good. Posterior pituitary. Antidiuretic hormone comes from the posterior pituitary. There is a adrenal hormone that does target the kidneys, but it's not antidiuretic hormone. We'll review it in about 2 minutes or less. So the descending limb of Henle has the ability to take water from the filtrate and put it back into our blood, so it can conserve water if we need to. Any water is not reabsorbed from the filtrate here, travels now to the ascending limb of the loop of Henle. So I want you to draw your arrow and label this. And what's happening here at the ascending limb of the loop of Henle? Reabsorption of sodium, maybe potassium. Chloride, it may be, I can't recall off the top of my head, but some ions certainly will be reabsorbed here. Ions not, what is not reabsorbed here? Water. So the ascending limb of loop of Henle has a bunch of ion transporters, so we can reabsorb our ions. Which hormone could then target the ascending limb of loop of Henle? Aldosterone from our adrenal cortex. Be sure to throw the gland on there in the prefix, okay, but you're right. Adrenal cortex can secrete aldosterone. We learned to target our kidneys to reabsorb specifically which ion? Sodium. And it actually secretes which one? Potassium. Same concept. Anything that's not reabsorbed still continues in the filtrate. The next landmark area that will be addressed or entered would be what's our next area? The distal, you can call it the distal tubule, you can call it the distal convoluted tubule, which is over here. Distal means further, right? So we're getting further away from the glomerulus. And that distal convoluted tubule. What is, right, it spans basically from here, this whole thing would be the distal convoluted tubule. What's happening as fluid travels along? Let me restate that. As filtrate travels through the distal convoluted tubule. What did you say? I just can't hear. In what fashion? What are we doing? Yeah. Expelling. So what word do we use for expelling? We're going to secrete. At the distal convoluted tubule, there may be some secretion. I haven't used that outside of the lab yet. So what does that mean for secreting something? What direction as far as blood filtrate? Where is it? It's going into the tubule. Okay, it's going into the filtrate. If something is being secreted, it's secreted into the filtrate. So it's kind of a last-ditch effort to put excessive things or toxic things, like, oh, you go in there, right? And so transport it into the filtrate. But there may also be what happening here. Still, there may be reabsorption going on. So maybe taking out good things and putting in excessive or waste products over here at the distal tubule.
Would it be mainly like sodium with water? I mean, I kind of found water.
Yeah, you can certainly still see some more water reabsorption, ion reabsorption. The nutrients should be pretty well picked off at this point, like your glucose most notably should be kind of reclaimed way back at the beginning. So it'd be more ions and lipid-soluble substances. they may be your hormones, even though we need to retain them, they're still lipid soluble, so they could still secrete into the filtrate just because they're just diffusing down their pressure, right, their concentration gradient.
Medicines, like
If they're lipid soluble, yeah.
some of them, like after it goes through your system, it goes out into your urine.
Yeah, so if you supplement, like a vitamin, for example, because you've got so many vitamins in your blood, you're just above set point, so your body's going to filter it and not reabsorb it. But if it's something lipid soluble, like you're on steroids for your sinus infection, steroids we know are lipid soluble, right? And so even though you need them, they're just going to diffuse, right? And so you could test them in your urine, right? You'll be able to test those. And go to the pregnancy test. What do they have you do all the time? Something in a cup, because our steroids are lipid soluble and they could be secreted into the urine outfit. So yeah, it could be a pharmaceutical that you take, whatever the case may be. Depending on solubility and just the concentration of it, maybe secreted. Or never even, maybe filtered and never even reabsorbed, actually. And probably just get rid of it completely. Good. Does that answer your question? Any other questions?
I have a question.
Uh-huh.
And the book that says that it secretes hydrogen potassium. How do you write that?
I guess I have no idea. It says hydrogen dash.
Hydrogen potassium, like that. And I was like thinking, maybe that's something else. So.
No, it must be just in the not ionic form, because they're both positively charged, so maybe just the atomic and just a molecule, unless it's bound to water. I'm not a chemist, so I'm gonna, my cards are shown, I have no idea. HK is the way I'd write it, but I don't know, that's probably wrong. So, it's like some of the other chemistry questions, so. The world's not over if you have to take chemistry classes. Yeah. Oh, that's something you need to take to Dr. Slagle and Dr. Z. Yeah, I would just say HK, but I don't. The balance and stuff doesn't make sense. I have to look at it. Good question. You guys are asking me some hard questions today, so lighten up on me. It's the last thing. All right. So filtrate, we can reabsorb and we can secrete substances as well. By the time it gets to the distal convoluted tubule, it'll enter into the what? What's the next thing? The collecting duct. Where there still may be reabsorption, there still may be what? Secretion, but it's very minimal. The exchange is not near the magnitude like we see through the rest of the tube. But it could still happen. So we could still refer to it as what? The fluid we would refer to as filtrate. I would still call it filtrate in the collecting duct, so we're still kind of processing it. We're taking out water, putting in whatever the case may be. But once it's at the end of the collecting duct and starts to drain into that renal pelvis, we're not going to process it anymore. It's gone. Your body is getting rid of it. It's going to go store it in the bladder until it's time to get rid of it.
So once it hits the collecting duct, then is that what you said?
At the end of the collecting duct. We can still process it a little bit in the collecting duct. So
Is the end the minor?
yes, the minor calyx. Because there are other nephrons draining into it. So it's collecting filtrate for multiple nephrons. So the collecting duct itself drains, I guess I can't say any different, it drains multiple nephrons. So the entire nephron itself spans from the capsule to the end of the collecting duct. And then the end of the distal convoluted tubule, and then that collecting duct would pick up filtrate from multiple nephrons. Additional questions about the tube component of our nephrons? I'm going to skip over the juxtamedullary versus cortical nephrons. We have about 7 minutes, and so I'm going to kind of get to the chase. The next thing I want to do is not necessarily define the juxtaglomerular apparatus. It's important, it's very important, but we just don't have time. But while we're at this image, figure 18.5, I want to visually kind of point out what's happening here. This is at the glomerulus, those capillaries that do what? Filter. But do not what? Reabsorb. Please make a note that the glomerular capillaries filter only. They do not reabsorb if your kidneys are healthy. We want them to form filtrate so we can process it. If they filtered and reabsorbed, it's futile, right? It's just like any other capillary in the rest of your body. But I like this image. One, structurally it looks really good. But two, it also shows that diameter difference between the afferent and efferent arteriole. The diameter is largest in the afferent and least in the efferent. And therefore, it's like a traffic pressure jam. This is what makes sure those capillaries filter and don't reabsorb. Because blood's entering at a high pressure, but then it's like a sieve. It's backed up. The only other outgate is diffuse across, filter across the capillaries. Are y'all able to see that? Okay. The next thing that I want to address for you guys is on page 5. What we'll do is just summarize those 3 phases of urine formation. And you can check your work right from your handout as well. Figure 18.7 oversimplifies the process of urine formation. So we got our glomerulus capillary. This would be the afferent arteriole. This would be the efferent arteriole. Anything in my capillaries would be considered which fluid? In my capillaries, I would call it plasma. Very good. Anything in my tubes, I would call filtrate. To form that filtrate from the plasma, though, the first thing is to filter. Okay. I've seen something like on the pre-labs filtration. I'm not sure that's a word. You laugh, and then your paper. Filtration. Filtrate. The process of filtering or filtration forms for us filtrate. On filtration, let's acknowledge it's just like any other capillary where lipid-soluble substances and our small substances can be filtered out. But what is not filtered out? Proteins and sugars get filtered, actually. The plasma gets filtered. That's where our lipids are lipid-soluble. They can filter as well.
I remember reading proteins were filtered out.
Big proteins are not. Big proteins, remember, go back to our capillary structure. If our proteins are so big, they can't fit through those little gaps, if you will.
Since the plasma is
Our red blood cells. Plasma protein free means no proteins.
Right.
So we do not filter proteins, and we do not see any red blood cells because they are just too darn big. So big substances that can't fit through the little holes of your capillaries stay in the plasma. Your red blood cells stay in there, big large proteins stay in the blood plasma. But our lipid-soluble substances, ions, and even our sugars do get filtered. But even though they're filtered, the next thing, what are we going to do with them? Let's say I've got a bunch of glucose and I had a big yummy meal. That glucose gets filtered and then reabsorbed. Okay, so the second phase for urine formation is reabsorption, where we know something from the filtrate is going back into the capillaries, and more specifically the paratubular capillaries, not into the glomerular capillaries. We also know filtrate can be added to, and the process is called what? Secretion. The third major phase of urine formation is secretion, and we see that in higher proportion along that distal convoluted tubule, getting rid of excessive or actual waste product, putting it back into the filtrate. Once processing is done, then what can we do with the secrete it? Proper word, sorry, excrete it. I will hold you accountable for these phases. And chapter 19 looks at the hormones. I want you to at least be familiar with which two hormones? Aldosterone and antidiuretic hormone. Renin, I promised you all semester we would talk about it. We did not. So don't be so sad, but it'll be okay. But it's a cool pathway. Be curious about it. Any questions before we conclude?
So we need to know aldosterone and
Antidiuretic hormone.